everybody! Today we get to play with fire. Minimally, that's not really the point. So anyway, the LO for this video is 5.7. The student is able to design and or interpret the results of an experiment in which calorimetry is used to determine the change in enthalpy of a chemical process, which is heating, cooling, phase transition, or chemical reaction at a constant temperature. So basically, you can figure out the change in enthalpy by creating an experiment in which water gains heat and a different substance loses heat. So the purpose of this experiment is to find the specific heat of a metal using calorimetry. And you could Google that, but you don't get to play with fire, so then it's like not as cool. Anyway, so materials for this experiment are obviously a Bunsen burner and matches, but I suck at lighting stuff, so it's already lit. Tongs, previously weighed out zinc. It is 15.54 grams. It's a lot of zinc, but who cares? Here's the zinc bottle. 2 thermometers, a cover for the calorimeter, our bootleg calorimeter, watch glass, test tube, deionized water, beaker, and more deionized water. Because where's the fun of that? So first, you would weigh the zinc, but I've already done that. And then you're going to place it in the test tube carefully. You know what, I'm just going to scoop this up in my hand. This is not proper lab technique, but whatever. It works surprisingly well to not be proper lab technique. There we go. I'm going to put that off to the side. I've already measured out 200 milliliters of water, and so now I'm going to take the initial temperature of the water. And it is 23 degrees Celsius. Okay, write that down. And then I'm going to heat the zinc using the tongs. Probably a better way to do this, but I do not know it. So here we go. Yeah, I got this. Yeah. Take it off for a hot minute. I get it hot because it's been heating. Alrighty. It has stopped at 140 degrees Celsius. That is some very hot zinc. So anyway, we're ready? Yeah, can I touch this? No. Obviously you cannot pick it up. Try this one. I'm gonna pour this in here. Ah yes. I'm going to quickly cover it with this shebangs. Doesn't lose any heat. Wow. Then you wait a very, very, very long time. So the wait is over. Not for Game of Thrones though. Anyway, the new temperature is 24 degrees Celsius. So the water only raised 1 degree, which is kind of lame. But that's okay. You guys still got to play with fire. So yeah, that's it. Data analysis in a minute. So for data analysis, the goal is to find the specific heat, and you can see by these equations here that there's a relationship that exists between the material and the water, and that the mass of the material times the specific heat of the material, which is what we're trying to find, and the change in temperature of the material equals the negative of the mass of the water times the specific heat of the water, which is 4.18 joules per gram Celsius, times change temperature of the water. And the reason it's negative is because the material is losing heat, which will make delta T negative. So if you look over here, because you need the mass of water, but we only measured the milliliters of water, but the density of water is 1 gram per milliliter. So you have X amount of milliliters times 1 gram of 1 milliliter, you're going to have X amount of grams. So using our data that we had 200 milliliters of water. I'm going to go ahead and write that in there. 200 milliliters of water times 1 gram over 1 milliliter, obviously, is 200 grams of water. So now that we know the mass of our water, which you can see up here is 200 grams, you can go ahead and put that in right here, 100 grams, and you can go ahead and fill in the mass of your material as well from your data table, and that is 15.54 grams. So just go ahead and put it in here. Okay. So now we're on to the change in temperature, or delta T, and when we measured it earlier, we called it 24 degrees Celsius. But after a few more minutes, it actually lowered itself to about 23.8 degrees Celsius. So we're going to use 23.8 degrees Celsius as a nice approximation. So we have the initial temp of the zinc, which was 140 degrees, and we're going to subtract the 23.8 degrees. So you can do it over here. 140 degrees minus 23.8 degrees gives you 116.2. So we're going to go ahead and use that in here, as you can see there. And we're going to do the same thing with the water, but we're going to do reverse. So we're going to take 23.8 minus 23, which was the initial temperature of the water. So go over here, go 23.8 minus 23, which is the initial temperature, 0.8. So now you do some moving. Haha. There are arrows drawn to kind of indicate where you're just going to go ahead and move things to. So you're going to go ahead and move the 200 over here, move the 0.8 here, and your change in temperature for your material and your mass of material are actually going to go under it, because you're going to take these, because they're all multiplied, and divide this by them. So you're going to go ahead and do that now. And at this point, the negatives cancel each other out, so you're left with positive value, which is good, because otherwise, your CP can't be negative and all that jazz. So just plug it into the calculator now. So as you can see here, once everything was multiplied together, it gives you a value of about 0.37037, which was significant figures, because that 0 is counted as significant, 0.37. Yeah, so now we do percent error. So we've set up our percent error equation. The 0.39 is the accepted value for the specific heat of zinc, which is the metal we used. So you do your experimental value minus the theoretical value, and put that whole thing over the theoretical value. Then you take the absolute value of that, because it can be negative, you could have gotten higher value, and you multiply it by 100 to get your percent. So we're going to do that now. And then with significant figures, again, it will turn into 5.1%, which isn't that bad. It's actually really, really good. So, yeah, that was all. Thanks for listening for an extremely long time. Thanks.